So first question here. It says that the Monarch Marching Band is selling tacos and burritos to make money for a trip to Washington, D.C. Now, to make enough money to afford the trip, the club must sell at least 10 burritos and at least 30 tacos every day. Now, because of limited space, no more than 40 burritos or 70 tacos can be made. The total number of orders cannot exceed 90. If profit is $1.65 per burrito and $1.05 per taco, how many of each item should the club sell in order to maximize profit? So this end goal here of maximizing something, in this case we're maximizing profit, is what the linear programming process can be used for. Now, as you probably can see here from this intro, there's a ton of information given to us in this problem. This is like a big paragraph word problem. But we are going to go through this carefully, grabbing out all of the different pieces that we need. So the first part of this process, this is no different from when we approached our word problems last week with systems of equations, is we're going to assign our variables. You always have a choice on this. You can use x and y as long as you write out what they represent. I am going to use letters here that remind me of what they represent, and so to help figure out what the two letters should represent, I'm going to look for the how many question. So let's go ahead and circle that, or underline it, or highlighter if you have a highlighter. How many of each item should the club sell? So we want to figure out how many burritos and how many tacos. That's what our variables are going to represent. So I'm going to have a B represent the number of burritos. And then I'm going to have a T represent the number of tacos. So using these letters can help to remind us of how each piece is connecting back to the context. Okay, let's take a look now at the second part. So the second part of this process is to identify the constraints. So constraints are things that we are limited by. These are like restrictions in the problem. And so the type of words that we're looking for when we're identifying our constraints are words that would imply an inequality. What we're going to see here is that every constraint is going to be written out as an inequality statement. So when we look back at the word problem and we look for some of those words, it says here that they must sell at least 10 burritos and at least 30 tacos. Okay, so that's going to be an inequality. So it has to be at least 10. It could be more than 10, but it has to be at least 10 or at least 30. Some other inequality words are, right here we have a limitation on space. So because of limited space, no more than 40 burritos, no more than 70 tacos could be made. So anything that we are limited by or restricted by. All right, so we have three constraints here that we're going to list out. Sorry, the other one that I forgot to grab up here in the problem was this one down here. The total number of orders cannot exceed 90. It has to be less than or equal to 90. So you'll notice that these three constraint statements have been listed out for us here below. And what we're going to do with each one is translate the information into algebra. We're going to translate it into an inequality statement. So let's start with the burritos. If we have to have at least 10 burritos, but no more than 40 burritos, that's going to look something like this. We can actually write that one as a compound inequality, where the number of burritos has to be greater than or equal to 10, so I'm going to put that on the left side. At the same time, no more than 40 burritos means that it would be less than or equal to 40. So this statement here is telling us, okay, the number of burritos has to be in between 10 and 40 burritos. We're going to write a similar statement here for the tacos. So I want you to try this one. It says that we need to have at least 30 tacos, but no more than 70 tacos. So go ahead and write in what would that second inequality be. All right, so really similar to the first one, but we have T represented in the middle here for tacos. Greater than or equal to 30 means at least 30. At the same time, less than or equal to 70. All right, now the last one, the total number of orders. So that means the total number of burritos and tacos all together cannot exceed 90. That means it would have to be less than or equal to 90. So let's say the total number of burritos plus the total number of tacos, so we have B plus T is going to be less than or equal to 90. All right, so constraints always involve an inequality statement, and they always represent something that is required or that we are limited by. So we have actually dealt with a lot of the information given to us just in writing out the constraints. The next piece of getting this problem set up is writing the objective function. So if you look at what's written down here for that next step, the objective, that is another name for the goal. So the goal here is that we want to maximize profit. So that's typically told to us probably near the end of the problem. So when it said how many of each item to get the most profit or the maximum profit, that's what we're wanting to write for the objective function. So here it's really the profit function. So this is where we're going to take all of the information about profit and put that into an equation. Notice how the objective function is not going to be an inequality. And so I'm just going to write out the word profit, and here we're going to write an equation, so the overall profit equals. Now, remember back in the problem, it said that the burritos make a profit of $1.65. So we're going to do $1.65 multiplied by the number of burritos. And then the tacos made a profit of $1.05. So we're going to do $1.05 multiplied by the number of tacos. All right, we're going to be going back to that objective function in a few minutes. But the next step here, when we're taking a look at the graph, we are only going to be graphing the constraints. So we're going to put those constraints together as a system of inequalities, just like what we had yesterday, where we're going to see where the shading is for each one, and then we're going to see where all the shading overlaps. So you don't have to recopy this on your paper, but I am going to rewrite those inequalities off to the side here so that we can see them. So we have number of burritos constraint, number of tacos constraint, and then a total number of orders constraint. Okay, you'll notice that our graph here, the way this is set up, is that we have our burritos labeled here on the x-axis, we've got tacos labeled here on the y-axis. When you are doing these on your own, you can choose how your axes are labeled. So it might not be labeled for you at the very start. If that's not the case, then you're just going to pick one. Before you make your graph, though, you need to either write out the words or at least write out the letter, especially if you're not using X and Y. Like this is the B axis and this will be our T axis. So that's how we can think about that. So let's take a look at this constraint for the number of burritos. So it has to be at least 10, but no more than 40. So where the burritos are, that's like on our x-axis, I'm going to identify where 10 burritos would be. That's right here. And this is going to be a vertical line going through the burrito value of 10. So that's one boundary point on the left side. And then we're going to do another vertical line here going through the burrito value of 40. That's the other boundary on the other side. Now, if you think about where the shading would be here, we only want burrito values that are in between those lines that we drew. Just like we did yesterday, I'm not going to actually shade yet, but I'm going to put in these little shading arrows to remind me of where the shading should go for that inequality. At the end, we're going to see where does the shading overlap. Okay, now for our next constraint, this is going to be for the number of tacos. So notice how tacos, that's like on our y-axis. So let's find our boundary points there. So for tacos, it had to be in between 30 and 70. All right, so I'm going to go ahead and find 30. And this time it's going to be a horizontal line going through that taco value of 30. And then we're going to go up here and find the taco value of 70. We're going to have another horizontal line there. And since it has to be in between 30 and 70, when we think about where the shading is going to be, let's put in those little arrows. Let's go ahead and show that the shading should be in between those two horizontal lines. All right, now let's take a look at the last one. So overall, the total number of orders cannot exceed 90. Well, I'm going to think about this one momentarily. I'm going to think about it as being an equation. So if we were to think of it as b plus t equals 90, well, that's like an equation that's in standard form because the variables are together on the same side. So we could find the intercepts. Even though we don't have x and y, we could find the b intercept and the t intercept for our two axes. So let's try that. If we wanted to find the t intercept, that's going to be when b is equal to 0. So I'm going to cover that up, and that would just be t equals 90. So the taco intercept is going to be at 90. And then when we find the burrito intercept, that's when the amount of tacos would be equal to 0. Well, if you cover up that one, you get b equals 90 again. So both of the intercepts are going to happen at 90. So let's go ahead and show that here. I'm going to find 90 on my taco axis and go ahead and plot a point. And that makes sense. If you think about the ordered pair of this, that would represent, well, you could have 0 burritos and 90 tacos. No, that doesn't satisfy the other constraints, but it does work for the last one. Well, if the total orders is equal to 90, like what if you just had all tacos? It was kind of like the CD and the book problem. Like, well, maybe you just buy all CDs and you don't get any books. That's the meaning of the intercept. Then let's go ahead and find that for the burritos. Now, here's something really cool to know. And by the way, that ordered pair would look like that. It would be like, well, what if we got all burritos and no tacos? Okay, so anytime you have it set up like this, where it's just the variables added together, no coefficients, no other numbers in front, when you get your intercepts and you connect them, this is always going to have a perfect slope of -1. So that's kind of cool. The slope of -1 is going to perfectly pass through the diagonal of all of our little squares. So I'm going to go ahead and connect them like this, but if you needed to get some other points, you could just use that slope, up 1 over 1, up 1 over 1. Notice how that's going to give me all of these like additional dots to plot. Sometimes it's a little easier than to connect it unless you have a ruler, if you have more dots plotted. Okay, so that's a constraint, so the total orders cannot exceed 90. Let's think about where the shading would be on this one. So yesterday we talked about using the test point of 0, 0. When you plug 0 in for each variable, we want to look and see if it makes our inequality true or false. Well, in this case, if we plug in 0 for b and we plug in 0 for t, we end up getting 0 is less than or equal to 90. Is that true or is that false? That's true. Okay, so what direction should we shade? Should we shade above the line or should we shade below the line? Shade down below, yeah. So 0, 0 would be right down here in the corner. If you want to draw a little label there just to point out where that is. So when we plug 0, 0 in, if it made it true, that means 0, 0 is a solution. All the other points in the same region are also going to be solutions. So let's go ahead and do our little arrows toward 0, 0. It's going to be kind of below the line. Okay, and then I want you to look at your graph and identify what is the little section where all of the shading overlaps. And I want you to go ahead and shade that section in. It's going to look kind of like a geometric type looking shape. Okay, so I've shaded mine in. I also used a little bit more of a bold line to kind of mark the boundary, so we make sure that we don't have any shading outside of that. Now, that shaded region actually has a special name, and I would like you to label that here. This is called the feasible region. Now, let's pause for a moment here and talk about what this graph is showing us. What is this graph going to allow us to do? Well, remember, our whole goal is to figure out how many burritos and how many tacos are going to give us the most profit. We had all of these constraints. We had some restrictions, we had some limitations, we had some requirements. Well, every single ordered pair that is inside of the shaded region meets all of the constraints. It meets all the limitations. So for example, if you were to pick a point somewhere right in here, that would be 30 burritos and 40 tacos. Okay, that's a possibility because we've met all of our constraints. We have a lot of other choices that we can choose in here. What we need to figure out is, okay, well, which one of those combinations gives us the most profit? Because each combination is going to be, if we plug it in here to our profit equation, it's going to output some dollar amount. Well, it turns out that we don't actually have to test all of them. The one that is going to give us our maximum is always going to be a vertex point at the edge. So if you look at the edge vertex point, the vertex is where like two lines cross, intersection points, we could think of it like that. We have 1, 2, 3, 4, and 5. The vertices, they're like the corners of the geometric shape. And so you'll notice here that we have a chart where we are going to list out those vertex points. And the reason that they're always at the edge is because if you think about picking a point somewhere in the middle, well, if you go further to the edge, like even if you had the same number of tacos, you might get more burritos if you go further out. So it's never going to be one that's in the middle. All right, so when we look at the vertex points, one thing that I would like you to do, always above your vertex chart, if you are using different letters other than X and Y, is to go ahead and list them out like you would X, comma, Y, but whatever was on the X-axis, in this case that's burritos, list that one first, and then like whichever one you labeled on your Y-axis, let's list that one out second. Okay, it does not matter the order that we put these vertex points in. Let's just start down here in the lower left. So if you look at this corner piece here, this is 10 burritos and 30 tacos. So we're going to write this as an ordered pair, 10, comma 30. Now, here's what I'm going to do is I'm going to test that combination. I'm going to see how much money that combination would bring in. So right here where it says profit, I want you to copy down the profit function. And I'm just going to use a P here to represent profit, but I'm just going to recopy it from what we wrote earlier. Notice how we're keeping everything in the same order. So notice how the B value that's listed first here, B comes first here in our equation, T was listed second, T comes second. That's a nice way to keep things organized. Okay, so here's what it's going to look like when I plug it in. And I might need a calculator. You might need a calculator when you're testing these combinations. So let's do $1.65 multiplied by 10 burritos. Let's do $1.05 multiplied by 30 tacos. All right, so when we plug that in there, the $1.65 times the 10 burritos, that's going to give us $16.50 from the burritos. The $1.05 times the 30 tacos will give us $31.50 for the tacos. Adding together the $31.50 and the $16.50, that's going to give us a total profit of $48. All right, so I want you to finish the rest of this chart. So go ahead and list out the ordered pair for the remaining vertex points. We're going to plug each one into the profit equation, and then I want you to look at answering this final question. We want to figure out what point maximizes the profit,
In other words, what combination of burritos and tacos was best for the rest of the profit. And you didn't have to write out the steps every time for what you plugged in. I wrote them all out just so that everyone knows and sees where we're plugging these numbers into that equation. You're also fine to just type those into your calculator and just write what you got for the profit. So that first profit we got at $48 actually was not very impressive compared to what we got with some of the other combinations. Notice that the highest one was 40 burritos and 50 tacos. So what I like to do here, once I identify which one is the most, is I like to just put a big circle around that. And it's helpful to do this piece right here of the labeling so that when we're listing out our final answer, we don't want to just say 40, 50. We want to connect this back to our context. So what does the 40 represent? Is it burritos or tacos? Well, it's in the position for burritos, so it was 40 burritos and 50 tacos. And then we also want to address what the maximum profit was. So in this case, our maximum profit was $118.50. And she needs to figure out how many muffins and cupcakes to bake. Well, both types of baked goods are baked in the same type of tin. Nashira only has 5 baking tins, which can hold 12 items each, and those could be muffins or cupcakes. So the total number of muffins and cupcakes cannot exceed 60. She also knows that she will need at least 20 muffins, and she sells at least as many cupcakes as muffins. Suppose Nashira sells the muffins for $2.75 and the cupcakes for $3. How many muffins and how many cupcakes will give the most amount of revenue? In other words, will maximize the revenue. All right, so reading through this new problem, I would like for you to try the first few steps here on your own. So I want you to start here with assigning variables, and then look at the statements that would end up being a constraint, inequality. So we're going to turn those into inequalities, and then the last one I want you to try here is that objective function, which this time we want to maximize the revenue, so it's going to be the revenue function. So I would say let's start underlining pieces, look for clues from that problem, and we'll come back together here in just a few minutes. All right, so let's start to look at our constraints here. So things that we're limited by. So one thing is that the total number of muffins and cupcakes cannot exceed 60. So we could have 60, we could have anything less than 60, but we cannot have any more. And remember, that's because there's only 5 baking tins. Each tin holds 12 items, 5 times 12 is 60. So for the first statement here, the total number of items altogether, M plus C, has to be less than or equal to 60. Okay, we are also told that I'm going to need at least 20 muffins. So the number of muffins, M, that's going to be greater than or equal to 20. So if you think about what at least means, well, at least 20 means, well, I could have 20, or I could have like 21, or 22, or 23, or 24. I just can't have anything less than 20. All right, so that's our second one. I think the third statement, I think that was the hardest one. And so I want to give you some tips for how you can think about setting it up. It says we need to have at least as many cupcakes as muffins. Okay, so when I first look at that, I'm going to think about testing this out with some numbers so that I can figure out the inequality. So I'm going to think, all right, if it's at least as many cupcakes as muffins, I'm just going to make up some number of muffins, like 10. Okay, so let's say I have 10 muffins. Well, at least as many cupcakes as muffins. I could have 10 cupcakes, right, because that's at least as many as I have muffins, so it could be the same amount. Or I could have anything more than that. I could have 11 cupcakes, I could have 12, I could have 13, I could have 30. That would be at least as many cupcakes as muffins. So looking at the numbers here, I'm going to do this in terms of cupcakes and think, okay, so the number of cupcakes has to be greater than or equal to the number of muffins. Equally, you could have said the number of muffins has to be less than or equal to the number of cupcakes. That would be a different way of saying the same thing. Okay, Then we have our objective function. So our goal here now is to maximize the revenue. So we're going to look at the information for how much they are being sold for. Muffins are being sold for $2.75. Cupcakes are being sold for $3. So overall, the revenue is going to be $2.75 multiplied by the number of muffins and $3 multiplied by the number of cupcakes. All right, so now we're going to go to that next step of graphing and shading our constraint inequalities. You'll notice that this graph, similar to the other one, has the variables already set up for us in terms of being labeled. So we're going to have n, the number of muffins, is going to be here on our x-axis. We have c, the number of cupcakes, here on our y-axis. All right, so let's start to go through each one. Let's look at the first one. So m plus c is less than or equal to 60. If both variables are involved, it's going to be a diagonal line. Let's think about getting the intercept because the variables are together here on the same side. It looks like the c-intercept is going to be 60. The m-intercept is also 60. So let's go ahead and find those endpoints here. The c-intercept is 60. M-intercept is also 60. Notice how it's going to have that same slope of -1. So we think about going up 1 over 1, up 1 over 1 to get all the way from one point to the next. All right, now when we think about the shading here, if you plug in 0, 0, well, 0 is less than or equal to 60. That is true. So kind of like the one that we did before, we're going to go and shade towards 0, 0. Okay, now the second one, this one's going to be a little bit easier to graph because it's just m is greater than or equal to 20. It's only one variable, so it's not going to be a diagonal line. This one is actually going to be a vertical line because it's going to go through the m value of 20, which is right here. So we're going to go ahead and draw a vertical line through the m value of 20, and if it has to be greater than or equal to 20, well, numbers that are greater than 20 are to the right, so we would be shading to the right of that line. All right, let's talk about the last one here. So we have C is greater than or equal to M. All right, so let me give you a little trick here, a way we can think about this. Notice how C is labeled on the y-axis, so it's kind of like our y variable. M is labeled on our x-axis, so that's like our x variable. Sometimes it can be helpful to think of our equation back in terms of x and y so that we can figure out what the graph looks like. So this is really like y is greater than or equal to x. And if we think about how we would graph the boundary line for this, momentarily we can turn it into the equation y equals x. We really only need the inequality symbol to figure out where we're going to do our shading. Now this is actually in slope-intercept form because this is telling us that it has a slope of +1 and it has a y-intercept of 0. So let's think about what that line would look like. So we start here at 0, 0. Up 1 over 1 to the right is going to be a positive slope. Up 1 over 1, and so on. So I'm going to continue all the way up here to the top. That's our line, y equals x. Okay, now here's the only problem when it comes to figuring out where we're going to do our shading. We actually cannot use the point 0, 0. We talked about this for a moment yesterday, and that's because 0, 0 is on the line. That's the one time you can't use that point. You have to get something that's either on this side or that side. You can pick. It doesn't matter what numbers you choose. It's often still easy to get numbers that are like somewhat easy to deal with. What I might do here, so I'm noticing it kind of looks like they're counting up by 5. It really doesn't matter what point you pick. This is just like a random selection here. I'm going to grab this point. It has like an x value of 20 and a y value of 5. I'm going to think about that point to test just because it's not on the red line. So if I were to plug that here into this inequality, so the y value was 5, and the x value was 20, let's think about this. Is 5 greater than or equal to 20? No, it's not. It's false. So that means that that point 25, that's not a solution. All the points on the same side are also not solutions. So that just means that our shading is on the other side. Now, if you would have randomly picked a point over here on this side and plugged it in and thought that it was true, you would still have the same conclusion, because then you would just shade toward that point. Okay, so now let's find this little triangle in the middle where all of our shading overlaps. We're going to end up with some slightly different shapes for that feasible region, depending on our situation. I would like to make mine a little bit in bold so it really stands out. Okay, notice that here we only have 3 vertex points. That's fine. We were actually given a little bit more space than we needed. Let's go ahead and make a note here that n is like our x variable, number of muffins. C is on the y-axis, so that's like our y variable. And I'm just going to go ahead and start to list out the vertex points. Sometimes I do this in a different order, and I'll find all the vertex points first, and then I'll plug them all in at the end. Looks like this last one, if we look at how it's labeled, it looks like it's going to be 30 of each, 30, 30. All right, to get our revenue, that's our objective function. So that's going to be 275 times M plus $3 times C. All right, so let's test our first combination, 20 muffins and 20 cupcakes. So I'm going to do 275 times 20 and $3 times 20. It looks like that first revenue is $115. Okay, then we have 20 muffins and 40 cupcakes. Well, that's probably going to be more, right? Because it's the same number of muffins, but now we have more cupcakes. That combination of 20, 40 is going to get us to a price of $175 revenue. And then the last one we're plugging in here is, okay, well, what if we just had 30 of each? Oh, it's close. That's a revenue of $172.50. Super close, but it looks like this middle point right here was the best. So I'm going to go ahead and circle that. When it says what point maximizes the revenue, we're going to say 3 things here. So we're going to say how many muffins, how many cupcakes, and what was the maximum value. So let's state that out here. So that's going to be 20 muffins, 40 cupcakes, and we had a max revenue of $175.